Hi friends, welcome back to the convolutional course in this video. So in the previous video we have seen what are linear block codes. Now here we deal with convolutional block codes. The only thing which differs is that this convolution codes they don't have most of the mathematical expressions. They only deal with the states and their respective transitions. That's it. Okay. So here we go. This is the general block diagram of the convolution encoder of 1 bit. So only 1 bit we are sending. These are the two decoders, two convolution encoder. So two shift registers these are, and these are encoders of the which is outputting two code words. So generally, whenever we transmit input bit 1, we get two outputs of codes. Okay. Now these convolution codes have certain terms to be defined, and those are very important terms, and these convolution codes they only depend on those two terms. One is that code rate. Okay, one is the code rate. Second is the constraint length. Okay. One is the code rate, next is the constraint length. This code rate is given by R K by N. Here don't get confused with the small k and capital K. Okay, I'll tell you. Small k is number of bits. Small k is number of bits input to encoder. Okay. Small k is number of bits which are inputting to the encoder, whereas small n is number of channel symbols. Channel symbols. Okay, and most important is capital K. This capital K denotes the constraint length. Constraint length of encoder. Okay. Now as you see here, there are this is a 1 bit encoder. So my small k is 1, and there are two symbol channels here. So 1 by 2 is my bit rate. Okay, code rate I'm saying. Okay. So then if this is the case, I need to know what are the codes. There is the relation between these codes and the code word. Whatever we are sending, C1, for C1 to be the output, I have xk minus 1, xk minus 2. Similarly for C2, I have xk minus 2. Okay, these two are the equations governing the input and the code words of the encoder. Whatever the representations of these convolution codes we do in the later part, those all depend on these equations. Okay. Most importantly, these equations they give us the relation between the state diagrams and the trellis diagram. Okay, so here don't confuse yourself with the k minus 1 and k minus 2 terms. These are the previous bits which we are giving to the input. So this is the present input which we are giving, this is the past input, and this is the past input of the past input. That's it. Okay, that means if I sent first, I sent 0, 1 and again 0. Now I am sending. This is my kth bit. This is my k minus 1th bit. This is my k minus 2th bit. Okay. So if I add those three, I will get the code word 1 and respectively code word 2. Okay. Now I will directly go to the representation of this thing. Now generally these convolution codes are widely used in satellite communication. Okay. And other digital communication parts wherein there is a requirement of error detecting and controlling. Okay. Now these convolution codes are mainly represented in three ways. One is the state diagram representation. There is a state diagram representation which is the basis for next two representations. Okay. The second thing is that tree diagram representation. The third thing is most important one and easiest one, trellis diagram. Okay, so I'll directly step into a first one called state diagram. Okay, now generally whenever I consider state diagram, then state diagram says that state diagram only we can draw to a state machine. Okay, you can see my video on state machines or merely state and most state machines, what are finite state and infinite state machines in my VLSI code. Or okay, so here state diagram is defined for a finite state machine. Finite state machine. Okay, this finite state machine is my convolutional encoder. Okay, now for this, for any state machine, it have 4 different states. Okay, I'll start with the 0 state, and similarly we have other 4 states 1 0 1 1 and 0. Okay, now we know that 1 bit input, 2 bit output, right? So my input may be 0 or 1. I have 2 cases, and my output is 4 cases depending upon the input. Now for the input 1, I'll draw it with the red marker, and for input 0, I'll draw it the transition with the blue marker. Okay, now I'll say for 1 input, so 0 input. Okay, now I'll start from the state, this state 0 0 state, and when I'm at state 0 0 and when my input is 0, then I'll stay at the same state. Okay, this is the how state machine works. This is my input is 0 and my output is also 0. Okay, now whenever I am at state 0 and my input is 1, I'll move to the 1 0 state. I'll tell you how we got the outputs. First we consider only the inputs. Okay, now I'll go to the, whenever my input is 1, I'll go to the 1 0 state. Now I am at the 1 0 state. Now whenever I get the input as 1, it moves to the next state, right? Moves to the next state. Whenever it encounters 0, it moves to the 0 1 state. Now again, whenever it gets 1 at 1 1 state, it is in the same state. Okay, now whenever it gets a 0 input, then it moves to the 0 1 state. Okay, now again, whenever I am at 0 0 state and I get a 0 output, okay, so these are the paths. One more path missing is a down path. It is 1. Okay. Okay, now these are the inputs. Now according to the equations which we have wrote earlier, I need to know the outputs of the or code words of this state diagram. Okay, I'll start drawing the table here. Now what are my things is that input and